Hey guys, welcome back to another episode of Simuleo. So, here's what happened. For some reason, I could not, for the life of me, load the Twitch website. So it took, like, maybe the past 20, 30 minutes or something like that for me to get the stream up and running. I apologize for that, but it's not really my fault, so, you know, that's how it goes. Let me think. What do we have to do here? So, today, as I mentioned yesterday, is going to be basically a writing day. We're going to be getting the Arcane algorithm archive up to snuff and getting it basically set so that when we put the video out on Saturday, I think it is, we'll already have an article up on the Verlet integration, and it should be relatively straightforward for everyone. I kind of like how this week went. It was rather relaxed. We got the algorithm done. Everything was implemented. The visualization was finished before even Friday. So tomorrow, I'll kind of decide what we want to do from there. We could do more of the scientific visualization library. There's still some stuff there that I want to clean up, make a little bit better, so that for future visualizations we can do cooler things, I guess. But I like the fact that these visualizations are interactive and stuff like that. It's kind of good. Okay, so how does the Arcane algorithm archive work? It is on Gitbook. So the way you work with Gitbook is you go to the local directory, you type in Gitbook install, and then Gitbook serve. It puts up a local server. So if we open the link here, we get our local server. Okay, there's one thing that I mentioned a while ago, that when you went to particular chapters on the Arcane algorithm archive, you'd have to refresh it for the formulas to appear. That is no longer the case. Let me see, what do we have here? Euler methods. Let me think. Unlike the forward Euler method above, the backward Euler method is an implicit method, which means that the result of that it results in a system of equations to solve. Luckily, we know how to solve systems of equations. Oh, okay. Well, it turns out I've already written a chapter on Euler methods. I didn't remember doing this, but apparently I did. I think Euler methods are also. Let me look these up. Euler methods. Man, I am so out of it. Hey, NNG. Also, Buttercake, thanks for coming in. Let me see. Euler method. This is numerical procedure for solving ODEs given an initial value. Can we consider this a force integrator? Maybe not. Yeah, because I think it's just an ODE solver, so I don't think we can put this in the same category. So, we're in the computational physics directory. I'm going to go ahead and remove some stuff that I put in there just a second ago. So we're going to remove Euler. This is what I did when you were not here. So Euler 2, Euler 3, sorry about that, .md, ls. And we should have something for Runge-Kutta. What is that? Oh, apparently nothing. I've put nothing in Runge-Kutta. Great. Is it in the archive? No, it is not. Okay. So I'm going to go ahead and commit these guys, ls. Since we have the Runge-Kutta file already there, even though it doesn't do anything, let's just go ahead and do git add, just so I don't forget, Euler.md and Runge-Kutta.md. Okay, so now they're sitting there, ready to be committed. Now we need to open up a new file, which is going to be for Verlet, so Verlet.md. MD. Great. Okay, now let me open up another terminal over here, since all this is doing is just refreshing the server consistently, so I feel like you guys will know what this one does. So let's open up another terminal, pull it down here. This way we have two up at once. Well, never mind. This way we have two up at once. I need to find a better tiling system. You know, I haven't decided the best way to do it. So projects, algorithm archive, and then we're going to cd into computational physics. Where are we? Oh, sorry, chapters. Come on. Chapters, computational physics, and that should be it. Now we should have Verlet in there. Now if we go into Tmux, yeah, I could. So let's do vi Euler.md. Okay, now here's one big problem I have with the way this is currently done, and that is that in order to get the mathematics on Gitbook, this guy right here, right? I'm going to have to use some sort of LaTeX-like editor, right? Also, why is there an extra plus in there? Interesting. I don't think that extra plus should be in there. I'll remove that in just a second. So, in order to do that, I need something like MathJax or something. So, to use MathJax, I need to basically, well, put $2 in front of whatever I'm going to do. That's not the problem. The problem is, in order to get MathJax to work, I have to put a very annoying header on top of everything, which is a pain. So I'm going to go ahead and put that in there now. Then I'm going to go into VI Euler and fix the error we just saw. So it should be down here. Yeah, there's an additional plus in there. So we do plus plus, and it should just be plus there. All right, this, do another git add Euler.md. Now again, if you guys are not aware, the reason I'm doing this is just so we have a written record of basically all the different algorithms we've done. And I think it kind of helps people understand where we're coming from and such like that. So I think we can probably get this entire article written in the time that we're here. So it shouldn't be that big of a deal. Also today's stream, because it started late and we're not really doing the typical programming that we normally do, will probably be a little bit more relaxed than the normal stream. So feel free to just talk about whatever you want in chat, even if it's not directly related to what I'm doing here. So again, writing days will just be, I want to stream them, I feel like, but we'll see how they go. You know, if people don't really enjoy them, then maybe we'll take them out later. I don't know. It's one of those things I haven't quite decided on yet. So let's do it. Let's go into the Verlet algorithm. At the top of every chapter, I put in, one second, these dependencies. These are things that you might need if you are going to, if you're going to read this chapter. So one in particular that I want is Taylor series expansion. So let's pop down here, open it up, put in the dependencies. Taylor series expansions, I think is the only one I'm really going to want here. Yeah, that's about it. Yep, good. Okay, so now if we write this, all we have to do is update the summary. I can quit over here. So VI, I think it's a couple directories back. I'm going to say it's here. Where are we? Dang, I went one too far. Summary.md. And under computational physics, where are we? Euler methods. Yep, I want to yank paste, and I want to put an additional guy here, which is going to be Verlet integration. Integration. Then we're just going to say Verlet.md here. If we write and quit, it should update the server. So if we refresh, or not, if we refresh, we should see Verlet integration there. Great. Okay. So now let's get started. The Verlet.md. So first, let's go ahead and put in. Oh, where are we? Let me take a look at what I did otherwise. So let's go into VI Euler.md again. Yep. So then we should just be able to put here Verlet integration. Okay, so that's the start. Now we can go ahead and start writing. So where do we want to start with Verlet integration? I would say we start with the kinematic equation. So, how about we say, yeah, see, this is the problem with writing, right? It's kind of awkward if you don't know what you're doing. Anyway, so you guys all know Verlet integration because it's what we've been using for the past few episodes. If you don't, feel free to let me know in the chat and I'll talk about it as soon as I can. Okay, so Verlet integration is essentially a solution to the kinematic equation for the motion of any object, which can be found with a Taylor series expansion. And I'm going to go ahead and say that this will be linked here. So I'm just going to go ahead and put a link in here. And then I'm just going to put the equation in. So let's go ahead and do that. 2b. 1, 2, 3, 4. Pop it in here. It's a little bit different than how you typically do LaTeX for just typical LaTeX, but that's okay. So we're going to say x is going to be equal to x naught plus v naught times t. And I guess it's just going to be v naught t plus frac of 1 over 2. Then we want to do a t raised to the third plus frac of 1 over 6 b t to the fourth. And that should do it. So if we write this, take a look at what it says. Well, give it a second. Has to load. There we go. So we have what we have. Where where now we have to write what everything means, and this is what I forgot how to do over here. Okay, good. Where I guess we'll just say x is the position, the 1 second is the velocity, a is the acceleration, b is the often forgotten jerk term, and t 1 second is time. Now let me see, I'm also going to put higher order terms in here, so let's do big O notation. How do you do big O notation? Let's go into VI. I'm going to say it's back in computational mathematics, and let's go into FFT. FFT Gulituki. There we go. And I want to do O. So where's the big O here? I know I put it in here somewhere. 1 second. Let me take a look at that chapter. And we're going to go from there. So, why are you not working? That one equation needs to be updated. You forgot the second after the t. Yep, I will update that in just a second. I also need to update that equation in the Gulituki example. So where are we? We are here. Let's go ahead and do that now. Okay, and then we'll add that in there. I know I put big O notation somewhere, but let's go ahead and add it in the second t while we're at it. Thanks, Buttercake. Okay, so now what's next? We fixed that equation. Where's big O notation? I know it's here somewhere. I also need to update this chapter anyway, because, you know, Gulituki. Oh, sim O log n. Wow, okay, there's a lot of errors in here because of the, there's a difference between using this for regular LaTeX and using this for Markdown LaTeX, I guess. It's kind of a little bit different. Okay, let's also fix that while I'm in the file. So let's pop down here. And let's see, I should need... Let's look for sim. Yeah, there we go. There. And of course, there. Okay. So I'm going to go ahead and add that. Git add computational mathematics, and then Gulituki.md. Good. So that's added in. And I think I just used the big O. So let's just do plus O of t. Oh, I guess. Wait, what do you typically do for higher order terms? 1 second. Do you usually just do dot dot dot? I actually forget. Yeah, I guess it's just dot dot dot. Fair enough. So I guess I'm just gonna do plus. And is it C dots or L dots? It's C dots. Where are we? Plus C dots. C don'ts is not C dots. Write that. See what it looks like. So FFT should be fixed. Let's go ahead and refresh that page. Let me see. Do we see any weird dollar signs or anything appearing anywhere? Nope. I think it's okay. Good. And now let's go back to the Verlet integration. Yep. Seems good to me. T is time. Great. This CDOS is vertically centered. Wait. Oh yeah. It's centered along up and down. That's exactly right. Hey Zadison, thanks for coming in. Okay. So now what we're going to say is, let's say this equation is one of the most, or is a central equation to almost every physics solver, Newtonian. And brings up class of algorithms known as force integrators. Depends on the function in question, I think. Also, big O of the remaining terms. In this case, it might be t to the fifth. Yes, that is true. In this case, the big O notation of the Verlet integration non-velocity form is OT to the fourth. It should be. In a class of algorithms known as force integrators. So let's see. I'm going to do. Oh, how do you do this? Text force integrators. Let's see, should be something like that. There we go. Okay, the first force integrator. Let's see. I love how you correct yourself 3 times. I still wrote the equation. I do that so much in source code. Yeah, that basically happens all the time. Oh, I see what you're saying. Of the remaining terms depends on the function in question, I think. Yeah. So here, I'll show that in just a second. But here what I was doing is I was just saying, here, let's go ahead and write it and pop it up over here. Is that we have additional terms going forward. I wasn't saying that they are of any order. However, when I do the Verlet integration later, I'll show that why it's t to the 4th when we're there. So let's go ahead and dd here. And now this is one thing I don't like about Markdown, but it's how it has to be done. Markdown, you have to make sure, paste it there, and there. Good. dd, shouldn't be that 1/2 at squared. Yep, that's squared. You're totally correct. That's me for not reading correctly. So let's go down here. The first one of the first force integrators to work with is, let's just put here, Verlet integration. Should be, yes, you're totally correct. I appreciate that. There. Good. Okay. G. Which you can probably replace with OT. I could, but I want to keep the jerk term in there because of what we're doing next. So, Verlet integration is essentially a solution to the kinematics equation for the motion of any object, which can be found with a Taylor series expansion to be. I need the jerk term in there because without the jerk term, it doesn't make sense that the order of the error is OT to the, or O to the 4th. OT to the 4th. Wait, where's my... Okay, good. Okay, so what do we have here? So let's say we want to solve for the next time step in X. That might look like this. Wait, buttercake. What was your hint? That I still got the equation wrong? I'm sorry, I didn't get the hint. Yeah, my bad. So we're going to say x of t plus delta t. And I guess delta will be delta t. And what I need to do is make all of these functions of t. So we're going to say t. Oh, sorry about that. Another t here. There. And... well, no, I think it's okay to leave the functions of t out here, just to show it down here, and that should be okay. Yeah, we'll see what this looks like. So t plus delta t. It's always good to have another set of eyes when you're writing. Yeah, or a lot. Yeah, hence why I'm pointing it out again. Wait, did I miss something? Oh, the t to the 4th. Is this still the t to the 4th? It should be x of 0 instead of x not. Shouldn't that be x of 0? Why would it be x of 0? Sorry about that. Sorry, I'm not sure I'm following that one. So we'll say x of t plus delta t. Oh, I misspelled equation. Thanks. I was going to fix that one in. I can fix that one later. But appreciate it. Okay, so we're going to say x of t plus v of t times delta t. I guess delta t is there. Plus frac of 1 over 2. We're just not correcting it to mess with... I think... No, I got it. I'm so sorry. I didn't get it. I got it now. My apologies. So we're going to say a times delta t squared. So we'll do delta t raised to the 2. And then plus frac of 1 over 6. And then b delta t raised to the third plus, and now I'll say o t t to the fourth plus c dots. And in fact, I think you guys are right. Maybe I should put o t to the fourth here. Okay, something like this. So now let's write that, make sure it compiles just fine. Should be okay. Well, maybe. I just wrote it a couple more times. That probably was not what I should have done, but that's okay. Good. Yes, I shouldn't have a multiplication sign there, but everything else is okay. Let's go over here and do this. This would require, let's see, what do I have? For, this means that if we need to find the next x, we need the current velocity x, v, and a. Or people use o dot dot dot. I wanted to use both here, because again, so what's going to happen, right, is we're going to cancel this term and that term out in just a second. So after we cancel those terms out, it's going to be obvious why I have it in there. Well, let me just do it, and then we'll see in just a second. A, and then I guess we're just going to do etc. We need the current x, which is fine. However, we can do it with calculate x with less knowledge if we play a trick. Having dots doesn't really make sense. Wait, why not? 1 second. Okay, wait. Having the dots up here makes sense. So how about we keep the dots up here, and then we move down here and we say frac of 1/6. Yeah, then we just do this. And we say, next time say s, so let's say we can solve, and we say to a close approximation. That might look like this. There we go. Pop over here, and then say, capital T. Okay. So now we say, so let's say we want to solve the next time step in x to a close approximation. That might look like this. There we go. That solves the issue. Write that. This means that if we need to find the next x, we need to know the current x, v, a, etc., which is fine. However, we can calculate x with less knowledge if we play a trick. Oh, I see what you're saying. Yeah, that's probably true. But I wanted to say there is a term of order t to the fourth, so on and so forth. But that's okay. I think this is clear, what I just wrote here. So now we just say there are higher order terms here, and then we say here there is something of order t to the fourth there. And I think that's okay. We know that the, let's say we want to calculate x of the previous time step, again, to a close approximation. That might look like this. Okay, so now we basically copy this guy up here, except we put minuses where they're supposed to be. and that's going to be in front of this term and in front of this term. Now we have two. Wait. Now we have two equations. Wait, OT to the fourth doesn't make sense in this case because it can't be bounded above due to higher powers. Wait, what do you mean exactly? Oh, let's go up here and say t minus delta t because that's what it's supposed to be. Now we have two equations to solve for two different time steps in x, one of which have, if we add the two equations together and solve for x of t, x of t plus delta t, should be there. We find, let's see, should be here. It should be x, sorry about that, x of t plus delta t is going to be equal to 2x of t plus frac of 1 over, oh actually no, there's no frac here, a delta t raised to the squared plus, and I want to put O of delta t to the fourth. Okay? And the reason I want to do that, so, means we can find, oh, there's also another term I forgot up here. We want a minus x of t minus delta t. There we go. Let's go ahead and space this out appropriately. X. How about our next x? Simply by knowing our current x and the x before that. By knowing our current x, let's put a comma in here, x before that, and the acceleration. No velocity. Okay, so anyway, here's one of the big problems with the Verlet algorithm, which we talked about yesterday. No velocity necessary. In addition, this drops the error 2, and we'll say, oh, delta t, t to the fourth, which, where's these guys? Which is great. Okay, so let's go ahead and write this, and we should have basic Verlet integration up, and it should be okay. Yeah. 1 second, let me refresh it a couple times. There we go. Okay, misspelled delta apparently. B delta. Oh, I see the problem. Write that. Oh, but successive terms are always smaller because it converges. Never mind. Yeah, this should be okay, I think. Okay. So we say Verlet integration is essentially a solution of the kinematics equation for the motion of any object, which can be found with the Taylor series expansion to be x equals x naught plus v naught t plus 1/2 at squared plus 1/6 bt cubed, etc. Where x is position, v is velocity, a is the acceleration, and b is the often forgotten jerk term. Wrong delta? Yeah, probably where. Yeah, that is incorrect. Delta. I did it twice actually. So let's change this to a capital D and change that to a capital D. And good. Okay. One of the let's see, where are we? This equation is a central equation to almost every Newtonian physics solver. And let's go down here and let's change that to a capital N, because Newton's a dude. There we go. Newtonian physics solver, and brings up a class of algorithms known as force integrators. One of the first force integrators to work with is Verlet integration. Also, I think it should be OT plus delta t to the fourth, which resolves to OT to the fourth. Plus O delta t, I think. Let me think. Why exactly? Sorry, I'm not... Let me think about that. So the difference would be... Wait, didn't I just change that delta? Oh, I forgot to write it. Yeah, let me think. I think normally what they do with the... Let me look this up. Verlet integration. I mean, most of this, of course, can be found on Wikipedia. This is just kind of a simple way to think about it. Where are we? Usually they do this. That's usually what I see. Of course, the big O is different. I need to... How do I make that big O? I don't know. Sorry about that. Okay, so let's take a look at this. See what we have. I'm looking for big O. Minus, plus. Oh yeah, I have no idea where this would be. Empty set's probably not what I want. Geometry, delimiters, arrows, other symbols. Box is probably not what I want. You just math cal O. Let's see what do we have here. O. See what that looks like. Here we are. Yep, that's correct. Oh, thanks a lot. Okay, so let's go here and let's change all these to what we want to be. So let's add a guy here. And then we'll say math cal O. And we need to do that a couple more times because I kept using capital O for that. Paste here. There. And there should be one more over here. Yep. And we'll do math cal O there. And I think that's all of them. There's a few more in the Cooley-Tukey algorithm. Oh, sorry. Let's go into VI mathematics. And let's do Cooley-Tukey. And let's just look for capital O because I'm sure there aren't very many of them. Oh well, sim O. So I'm going to do math cal O there. And let's see how many more. Oh, that's it. Great. Okay, so now let's do the last get add, which will add that back, and we should be good to go. Okay, there we go. I think you should update the first equation to use function notation to keep things consistent. Yes, Twitch looks like it's fixed. Hey, Intrafist, thanks for coming in. You should update the first one. Okay, yeah, fair enough. I can do that. So we'll say x of t plus x naught. Yeah, these changed this to t. Yeah. This makes this literally the equation down there. Yeah, let me think. What do we have here? So if we do x of t, sorry about that. I mean, this again will literally be this equation. So we want to do, how about yank 3 yank, paste it up here. Oh, you want to do x not x of 0? Oh, I see what you're saying. X of t. Yeah, okay. This. that. Yeah, and change these guys to that. Yeah, that should do it. Okay. Yep, okay, that's fair enough. Okay, let me finish reading this then. This means that if we need the next x, that if we need to find the next x, we only need the current x, va. Oh, this means that if we need to find the next x, we need the current x, va, etc., which is fine. However, a and b shouldn't be functions because they're considered constant. No, remove the. Yeah, okay. That's a good question. Are they considered constants? Very good question. Because the acceleration could be dependent on the position. It's fine, it's fine. Okay. So let's go down here. We can leave it like this. I mean, everyone knows what we mean anyway. We'll probably get people talking about it. Okay. So, yeah, I think this is okay. Where x is position, fine. This means that if we need to find the next x, we need the current x, va, etc., which is fine. However, when we calculate x with less knowledge, we can calculate x with less knowledge if we play a trick. Let's say that we want to calculate x of the previous time step. Here it is up here. What? Oh, I'm pressing the wrong key. And the error term isn't dropped? Up here? The error term here. You want the error term there. 1 second. I don't want the error term there. Well, I just wanted to show that this equation continues forward, you know? Like, this is OT to the fourth plus OT to the fourth. I agree, but, here, let me leave it and let's have the discussion in just a second. I'm not convinced that we need to get rid of that, or that we should put no in that first equation. I kind of want it without the O, because without the O means that it just continually propagates forward, which is kind of what I wanted to show. There's some, yeah, it's kind of ambiguous too. Like, again, why do I have this equation and then literally this equation down here? I could just say, which can be found by this. The end result is x plus dt. Yeah, I mean, that's what we're looking for in the end. 1 second, let me get a sip of water. Okay. Verlet integration essentially, so, which means, yes. Yeah, I mean, yeah, I know the, wait, I'm confused. Are you saying down here? The error term definitely is not dropped. That's what I was saying. It drops the error to this. Which is pretty good. Because it means we skip, oh, I'm sorry, I did this incorrectly. I did this really incorrectly. Let me go up here and let me fix this. So we say, this should be, yeah, 1 second. It goes to, these should be delta to the cubed. I'm sorry about that. Oh, no. Yeah, so it removes the b term. Yeah, so the b term is now gone, right? And so now the error is just t to the fourth. Let me see. So let's go up here, and let's say, which is fine. So let's change the sentence. Here, and we'll say, however, because few people. Jerk term, our error is typically of order one second. Delta T cubed. I think that's what I want to say. That said, we can calculate x with less knowledge and to we play a trick and to higher order accuracy and to higher accuracy if we play a trick. Okay, that should be it. So here's what I meant to say, I think. This means that if we need to find the next x, we need to the current x, the a, etc. However, because few people calculate the jerk term, our error is typically t to the cubed. That said, we can calculate x with less knowledge and higher accuracy if we play a trick. And then the trick is this, and then it drops the error term to t to the fourth. That's what I meant to say, I think. So let's pop down here. With less knowledge and higher accuracy. There we go. Now, obviously, this poses a problem. What if we want to calculate it? 1 second. 1 second. Calcu a term that requires velocity, like the kinetic energy. Should be here, and we'll say it's frac of 1, 2 mv squared. Yep. Okay. In this case, we need the we certainly get rid of the velocity. Well, we can find the velocity to, let's say, where is it? Math, cal, O. Let's do delta T. Accuracy. By using the, I think it's Stormer, is it Stromer? Which one is it? I think it's Stormer. Stormer. And I think this is gonna have to be like, oh, how do you do umlauts and markdown? Okay, well, let's see what happens then. Which is calculate velocity like so. Okay, let's go ahead and write this, and let's pop down here. In Verlet. Thank you. Okay, let's pop down here. Yeah, so again, I'm not sure. We'll see how this goes. You know, so first things first, this stream started late because there were Twitch issues, so I'm sure people are still having Twitch issues. So I'm not going to be able to tell. I don't know if the writing streams will be worth it in the end, or if I should just take a day off to do the writing. You know, this is the thing I'm trying to figure out. So let me know if you appreciate the writing stream, or if you think we should just have this as a day off, and go just keep the keep this stream specifically for programming. This is up to you guys, totally your call there. So we're going to say velocity. I think it's velocity of, is it the next time step, or, yeah, v of t is going to be equal to frac. And let's pop this over to delta t. Hey, Slayer Darth, what's up? And we'll say x of x of t minus delta t. Oh, it should be t plus delta t. And then it should be minus x of t minus delta t. And I think that's correct. Let me see. Yes. Yeah, okay. And then I guess we can go ahead and add in plus mathcal of, oh, 1 second. Did you spill red wine over? No. This is my typical purple shirt. I like this shirt. I actually really like this one. So we'll say mathcal of delta t to the squared. Now, there's an additional thing here that we can do. That we can take the order down to delta t instead of delta t squared. This is actually pretty bad. However, it means that we don't need to keep the previous time step. We can just use the current time step. I feel like I'm just going to ignore this for now and just say that we can do delta t squared precision, and that's fair enough. If people want to know more, they'll know more. But basically, the only difference is saying, well, it's actually over here on Wikipedia. So this guy right here is ordered t squared, right? So x of t plus delta t minus x of t minus delta t here. And that's okay. But if we want kind of a worse approximation of velocity, we can just kind of turn this to x of t instead of x of t minus delta t. Why don't we have to put that over 2? Oh, and it's for the next time step here. So basically we can find the next velocity if we need it. And that's okay. Wait a minute, let me look at this equation. X of t minus x of t. Here we're basically, it should be change in x over change in time. Oh, and change in time is 2 because we have 2. Yeah, fair. We're moving 2 time steps, so it's 2 delta t. Yep, that's fair enough. So yeah, I'll put it in there. Looks hardcore. Well, yeah, this is fine. This is actually relatively straightforward. This is just how I do the writing. I apologize if it's still kind of weird. Okay, obviously this poses a problem if we want to calculate a term that requires velocity, kinetic energy. In addition, we can calculate the velocity of the next time step, like so. Okay, so we'll say here, and we'll say v of t plus delta t, and then we'll say equals hardcore. Actually, it's fine. We'll keep it. So we'll do frac of over delta t. Do you write all your to-dos in VI? I write pretty much everything in VI. I'm not gonna lie, it's my most used text editor. Every time I use other text editors, I get incredibly frustrated because I can't do simple things like yank lines, paste them, delete lines. It's just like, I just run into issues, and so I just use VI for everything. Like, it's kind of silly, I'm not gonna lie. So we'll say x of t plus delta t. And then we'll say minus x of t. Plus mathcal of O. 1 second. And then we'll do delta t. T. There we go. You're not cool enough for Vim? No, I'm not. I know. I'm sorry. I know, I'm trapped in the 1970s. I was going to write I wrote a script for a video where I was going to say how to VI, like how to use the VI text editor, and I was going to go through like all the things you need to do to use VI appropriately. And obviously, like, I started off by saying like it's from the 1970s, so if you really want to learn the history of VI and Vim, which you really should, you need to go to Wikipedia/editor war or whatever. and I showed it to them, and I wanted to show it to them in like links or something like that. I think I might have said this on stream yesterday or something. But man, I was really excited about that script. It was one of my favorite scripts I've written. But I'm probably not going to do the video for a while. Note. I'm going to put something here because it's not exactly obvious. Note that the 2 in the denominator comes from the fact appears because we are going over 2 time steps. It's essentially solving. Let me see. Yes, of course I want to hear a cool fact I might not know. That's story of my life. V equals change in t, so we're going to say change in x. X. Oh, actually, we're going to do frac. There. X over delta t. Should be right. However, this drops. The error for this is quite bad. Wait. You know, Nano was a fork of Pico, which was developed at University of Washington, right? I knew that they were related, but Pico is alias to Nano. Oh, I did not know that. So I knew that, like, all my Mac colleagues, they all use Pico instead of Nano. But yeah, that's actually quite interesting. I thought that they were just like, actually for the longest time, I thought Pico was like the Mac version of Nano, but I guess you guys are right. I guess Pico came first, which is weird to me. Quite poor. So we'll say mathcal of O. Then we'll do delta t, which is quite poor. Are VI better than Vim for you? This depends, right? Do I have Pico? Oh, I don't have it, but I do have Nano. Yeah, of course I have Nano. Everyone has Nano. Oh, interesting. Let me do Yawart Pico. And we want Pico is gonna be 19. So let's do Control D, sudo aura -a Pico. Yes. Okay. About VI and Vim. Here's the thing. Vim is the better text editor. If you're going to learn one of the VI or Vim family, learn Vim. Don't learn VI. However, I got used to VI, and now I just can't use Vim for the life of me. Every time I try to use Vim, I just fail miserably. Would you like to continue anyway? Yeah, okay, I'm not... I'll do this later. If I have a dependency issue, that's something I'll do later. So, if you're going to learn one of the two, learn Vim. I would argue that Vim is more useful than, in my opinion, many of the other text editors. Like, I'm very used to these text editors and I can get a lot done. But again, this could just be Stockholm Syndrome. It could just be that because I do stuff on the terminal a lot, I want a terminal-based editor, and because I want a terminal-based editor, my choices are Vim, Emacs, Nano, these type of guys, and Vim just, for me, is much, much easier to use than any of the other options for terminal-based editors. But that's my personal opinion. I mean, I guess R is written in Haskell because of the... Probably. Okay, so let's go ahead and write this. Check for... check the Verlet integration page. Okay, so... Well, that's interesting. What happened down there? V of t plus delta t. Wait, why is this just in a box? Okay. Note that the 2 in the denominator. Oh, that I wrote S instead of 2. Gosh darn it. I'm just not doing well, am I? Let's change this to a 2. Vim is VI with a bunch of stuff added to it, but I couldn't name anything. It's VI plus other colors plus split panes plus lots of other cool things. Yeah, actually Vim also has a help menu. Vim has literally everything you want. the issue I have with Vim is basically all the default settings that everyone sets up. It's just, I don't know, every once in a while, like, for example, in Vim, let me just open up Vim help.cpp or something. I don't know. Okay, so I think I have something set up so it's already color-coded. Okay, that's one thing I hate. For some reason, every time I press enter now, it automatically comments everything. I hate that. That drives me nuts. It's easy to fix, but it's still a pain, right? So you have to set your default settings right, and I don't know, it's just, if you're going to use VI or Vim, like, you know VI will act in a particular way, you don't have to worry about weird plugins. Vim, depending on who's using it, will look and act differently. I'm writing what I hope would be a quite cool Vim plugin. Anyone want to help me test it once I get it finished? Yeah, I might test it on stream if you want, but I don't know what it is. Yeah, I think it was enabled by default. Let me go into my vimrc. One second. Oh, I don't have a vimrc. What? How do I not have a vimrc? Vim info? What? I don't actually know where my Vim stuff is. It's supposed to be in your .vimrc, but I don't think I set one. You must have Vim 8? Maybe. Is that the latest version? It's probably what I have. Anyway, it doesn't matter. Let's go over here. Why is this in a box? Like so, v of t plus delta t. Wait, what? Why is this in a box? Oh, it probably just didn't compile. That's because frac. Let's do t plus delta t. Oh, it should be x of t plus delta t. X of t. That one should compile. Let's take a look at that. Oh yeah, it could be some natural default. I'll take a look at that in just a second. Yeah, there we go. That's beautiful. Okay, now we're going to go into etc vimrc. This is all commented out, I think. Do not load defaults if vimrc are missing. It must be some file that ships with Arch. Yeah, maybe. But here, if I also open this up and I do other things, this also bugs the crap out of me. The fact that these parentheses here are highlighted when you move over them drives me nuts. Because if I want to find, like, here's what I do in VI. I go to the parentheses here, like, and if I want to find the other parentheses, I just type the % sign, and it brings me to the other parentheses. It's easy enough. I hate doing this whole highlight thing. Like, it drives me nuts. It's just little things here and there that drive me nuts, just because I'm not used to it. Vim8 has default config file that ships with Vim, buried somewhere in user share. Yeah, fair enough. So let's do touch .vimrc, vim help.cpp. Yeah, this is better. But I think it still does a highlight. It still does a highlight, you know? That's still an issue. Things like that. Well, no, there's other issues too. It's just like random things that I expect to act a certain way. What are the big things? I can't think of any like really big things right now, but there were just a few things that kept popping up. Anyway, it doesn't really matter, right? Like, it's not that big of a deal. Okay. We're just quite poor. But works well, but gets the job done in a pinch. Okay. Wait, what happened there? Which is quite poor. Frac delta x delta t. In addition, we can calculate the velocity of the next time step like so. Let me see if I... in space addition. In addition, we can calculate the... I don't know why this appeared like that. Okay, let's just go ahead and get rid of that. Okay, so there's one last thing we have to point out, which is the velocity Verlet algorithm. Now, let's say we actually need the velocity to calculate. One second. Our next time step. Well, hey Lost Ender, what's up? Well, in this case, we need are the main second window without highlighting, cause it helps you focus more on stuff you do? I don't know. So for me personally, I don't use syntax highlighting just because I didn't get used to it, and it's not something I don't know. It seems weird to me when you're writing double and all of a sudden it gets colored, or you're writing a comment and it gets colored. I don't know. It's just weird. It's fine. I mean, I know what it means. It's just, it feels weird, you know? When you're not used to it, it doesn't make any sense. If you put set compatible in your vimrc, it disables literally everything. That's not VI. And since everything to work with VI, try that. Yes, almost everything. Almost everything is set back to how it's supposed to be, but not everything. So we do set compatible. I think that's how you spell it. No, set compatible. Set. 1 second. This is Markdown. How do you spell compatible? Compatible. Okay. It still doesn't match parentheses. However, it's still definitely VI because when I move up, down, left, right, it does this. So that's the thing. Like it doesn't do everything I want. I know because on the local cluster that we have, I set my vimrc to basically turn everything to VI, which is what I needed. My internet is dying. I'm gonna have to leave. Have fun. And NG, thanks for coming in. I'll see you around. Hopefully tomorrow. We'll see. We'll see what we do tomorrow. Actually, if you put set compatible with vimrc, I missed something. I don't remember. Is Markdown with MathJax, which allows us to do the LaTeX editing. We simply cannot use the above approximation, and instead need to use the velocity Verlet. 1 second. Where is it? Algorithm. Okay, so now next section on the velocity Verlet algorithm. We'll just put velocity Verlet without the algorithm. And I think I need to pop up here to the top. Yeah, good. Okay. In some ways, this algorithm is even simpler than above. Let's see. What do you use for math support within Markdown? It's called MathJax. And it's just used for like Gitbook or something like that. It does disable math parentheses if you put your vimrc, not if you set it manually, since match parentheses checks if compatible is set and doesn't load if so. Okay, well let's go into... Okay, look, I do use Vim for a few things, you know. So every once in a while you want to use Vim instead of VI. For example, there's a few things that you want Vim for. Vim can load larger files. That's nice. So if you have an incredibly large, you know, million line file, VI will not open this appropriately, Vim will. You know, also every once in a while you want, you know, certain things. So I don't want to necessarily set compatible in my vimrc right now. But yeah, you guys are all right. I mean, essentially all of my complaints about Vim are predicated with the fact that I know Vim is a better text editor than VI. Like, without a doubt, Vim is better than VI. However, I just got so used to VI, I just can't use Vim. That's how it goes, you know? You used to, like, if you're used to chopping down an entire forest with an axe, when you're given a chainsaw, you're kind of like, well, what is this for? You know? I like my axe. I don't know, that's kind of, that's the thing. Okay. We calculate everything like so. Okay, let me pull out my notes real quick. just to make sure I get the time and everything right. Where are we? So we'll say, okay, am I allowed to use multi-line equations? Have I done this before? Let me see. Thomas algorithm, maybe? I did. Look at that. Great. Okay, so let's see what I did for that one. VI, computational. I'm sorry, guys. Computational mathematics. And we want to go into Thomas. Oh, what did I name it? Oh, matrix methods. And then we should have Thomas in here. Yeah, Thomas. Great. Return to continue. Begin array. Great, 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 great. It's here somewhere. There it is. Begin a line. Begin. I'm really bad at like literally everything to do with typesetting. I always forget stuff. So now we'll say, right now we're using Markdown with LaTeX syntax. So the language, right now we're not coding, we're just writing up the Arcane algorithm archive, which is basically a notebook to keep track of all of the stuff that we've done so far. So let's go ahead and do it. We want to say x of t plus delta t ampersand equals. So this is just going to align everything appropriately. X of t plus v of t times delta t plus frac. How do you spell frac? There we go. And we're going to want to do 1 and 2. I guess we're going to want to put a t here. Maybe x t delta t t raised to the squared. Okay. I'm not exactly sure how to notate that a. Let's look at this in just a second and see what we think. So now we're going to say a is going to be equal to some function of x and t. And we're going to say v of t plus delta t. 1 second t. Does Markdown plus MathJax work only with Gitbook browsers? You have to enable it somehow on your system. And I'm not sure the best way to do the enabling. Let me see what happens if I just open this up in a Markdown editor. Just give me a second to do that. So let me write this equation and then I'll check that. It's going to be equal to, well, let's put an ampersand here. And of course we're going to have to add in the end line here. Oh, there's 2 of them. Ampersand equals, we want v of t plus. Oh, okay, I see. So we probably want a of t and a of t plus delta t here. Plus frac of 1, 2. And then we do a of t plus a of t plus delta t. 1 second. Oh, that was not the one I wanted to delete. A plus delta t. And then should be times delta t. Okay. Right, that. Let's take a look at what it looks like. We want to go to Verlet integration. Oh, that was not the right one. Verlet integration. There we go. X of t. Yeah, that looks okay. So we're going to want x of t plus delta t. So let's just pop here, and instead of saying it's a function of x and t, we're just going to say it's a function of x of t plus delta t. Okay, let's see what happens if we open this up in a text editor. So we're going to do remarkable verlet.md. Okay, seems to me that it's working in my is working for some reason, but I'm not exactly sure why. So it's working as you would naturally expect like Markdown to work, right? So let me just remove this and see what happens. Let's go here. Yeah, okay, so it's working like you typically expect Logitech to work. That is that, rather than, I don't know exactly why though, so let me delete this. Yeah, okay, so I guess you just need $2 signs for it to work instead of $1 sign. And then it works. Again, it does some silly things here. I don't know how to do it inline. I think maybe we can do it inline by doing the following. Let me try this. No, okay, I don't know how to put them inline, but it pretty much works. Do you want to save? No. Okay. Do you prefer Remarkable to other Markdown editors? Remarkable is just the one I've been using. I don't actually know so many other Markdown editors. For the most part, when I'm doing Markdown, I just write it in VI and then I look at it afterwards. So that's me. Okay, XAV, like so, which is literally the kinematic equation above with solving for, let's see, we want to do V, let's do X, V, and A every time step. You can also split up the equations like so. Okay, so let's just go ahead and grab these guys. It should be, let's see, 3, 6, 7. Okay, so here's the equations again, and we're just going to say yank, oh, how do we do this? I guess it's always A before V, X after V. So what we want to do is we want to do yank here, paste there, and then we want to remove this guy here. Add this there. And what we need to do is add in a 1/2 here. So we're going to do frac of 1, 2. And we're going to want to put that there, here, and I think here too. Okay, remove this frac here. Oh wait, I needed that one. Dang it. A of t plus delta t, and A of t here. And I think that's correct. Let's take a look down here. I give it a second to refresh. All right, there we go. Scroll down. V of t plus 1/2 t, yes, is equal to V of t plus 1/2 at. I probably don't need parentheses there. Times delta t. X of t plus delta t is going to be equal to X of t plus V of t plus 1/2 t delta t. A of t, yes, some function of X of t plus delta t, and V of t plus delta t is going to be equal to, yeah, this looks correct. I just need to remove some parentheses and then we'll be good to go there. We will X here, X there, and X here and there. There. Okay. Now we're going to pop down here and say, even though this method is more used than the simple Verlet method mentioned above, it unfortunately has an error term of, and let's just go ahead and put this in here, math cal O. That was not what I wanted. Oh, delta t raised to the squared, which is 2 orders of magnitude worse. Okay, good. That said, If you want to have any n-body simulator, the relay let's say, yeah, we'll capitalize it. Velocity relay algorithm is a handy choice. However, you may have to play further tricks to allow everything to scale appropriately. Okay, so one such trick is the Barnes hut. And I guess it's just going to be in here, so we'll just do Barnes hut. MD. Oh, that's not how you do it, is it? Barnes hut. MD. Barnes hut algorithm, which cuts the typical how do I put this? Cuts the complexity of n-body simulations from and I guess we're just gonna do mathcal delta t squared. Oh, actually, n squared. 2. And I'm going to put a sim here. And we're going to do the same thing. So let's do, grab this. And it should be n log n. Come on. Log n. There we go. Okay. However, you may, if you want to have an n-body simulator, I think I haven't described what an n-body simulator is. That if you want to have any simulator, how a simulation with many objects all moving let's see, if you want to have a simulation with many objects, all of which depend on each other, it's a handy choice. Yeah, maybe. These simulations body. These large-scale simulations. Yeah, I guess let me go here. These types of simulations are sometimes called n-body simulations. N-body and one such trick is the Barnes hut. Let me see if that reads correctly. Okay, so we have relay integration. Okay. Relay integration is essentially a solution to Kinetic's equation. Velocity, even though this method is more used than the simple relay method described above. Hey Romania, hey, what's up? Let's just do above. And let's fix these guys down here. Yeah, it's always math. Mathcal. Everything is math. And let's put another one here. It is a programming stream, but today is a writing day. I mentioned this yesterday and the day before. I kind of want to juggle a whole bunch of different things now. So on the one hand, I definitely want to do more programming, and I kind of want to shoot for one algorithm a week. So what I want to do is have do the algorithm on Monday, Tuesday, Wednesday, possibly Thursday also, and then have one day of the week set aside for writing, and that's today, this week. There will always be one day of the week set aside for writing, and my hope is that this kind of, I don't know, it allows us to keep kind of a notebook of everything we've done, because a lot of times, like, I don't know if this is a problem with you, but it's definitely a problem with me. We covered an algorithm the other day, like, for example, not the other day, like, almost 6 months ago, we covered, like, let's say the Lanczos method or something like this for finding eigenvalues. I did that back when I created the eigenvalue video. I don't remember how the Lanczos method works, but if I would have kept a notebook, I would have remembered, you know? So this is kind of part of that. I do have a notebook, but I feel like this is a better notebook. Okay, let's read this. Even though this method is more used than the simple Verlet method above, it unfortunately has an error term of OT squared, which is 2 orders of magnitude worse. That said, if you want to have a simulation with many objects, all of which depend on each other, the velocity Verlet algorithm is a handy choice. However, you may have to play further tricks to allow everything to scale appropriately. These types of simulations are sometimes called n-body simulations, and one such trick is the Barnes-Hut algorithm, which cuts the complexity of n-body simulations from O(n) squared to O(n log n). Yeah, this is okay, I think. I feel like it's kind of clunky. That said, if you want to have a simulation with many objects whose movements, all of which depend on each other, if you want to have a simulation with many objects whose motion all depends on each other, moving in each other's force fields, no, that doesn't make any sense. That said, if you want to have a simulation with many objects, all of which depend on each other's... if you want to have a simulation with many objects, all of which... if you want to have a simulation with many objects that depend on one another, let's say objects that depend on one another, depend on and we'll say like a gravity simulation, the velocity Verlet algorithm. See what that looks like. Refresh this page. Of course, the site can't be reached. Refresh it again and again and again until it refreshes, because that's story of my life so far. Just refreshing a page again and again, hoping that eventually something changes. Okay, like a gravity simulation. How do you do dashes in Markdown? Into M dash. I like to use 3 hyphen convention, but you're right, actual works just fine. 3 hyphens are used to delineate an H2. Okay, let's do 3 hyphens then. See what happens. And we'll write that. Okay, so I need to create the file for the Barnes-Hut algorithm. But I think that's about it. So we covered the Verlet algorithm, we covered the velocity Verlet algorithm. Both of these methods work simply by iterating time step by time step. Can be written, let's see, because they've written straightforwardly in any language. Well, we'll say that. So we'll say example code. Okay, can be written straightforwardly in any language. Have you ever thought about using functional programming? Yes, I have. I want to use Haskell at some point. I just haven't gotten to it yet. For example, here, for reference, here are snippets of code that use both the classical let's see, both the classical Verlet, classic and velocity Verlet methods, let's say, to find the time it takes for a ball to hit the ground after being dropped from a given height. Okay, now I'm going to go down here. I'm going to say to do. Okay. Functional programming is not like this. Okay, so I think this is okay. So let's take a look at what it looks like here. Example code, and I'm just going to put to do, and I'm going to leave that for the example code, and we will go from there. So I think this is okay to push online. So now I'm going to add one more method to computational physics, and let's go into vi Barnes Hut .md. And let me just pop up here to the top. And let's grab this guy. Well, that didn't work. Whatever I did didn't work. Oh, it's not pasting. Yeah, paste. There we go. So we're gonna have a couple dependencies. So let's put one dependency here, and we'll say dependency will be Verlet integration, and we'll just say Verlet integration here. I think it's just Verlet there.md, and I'm just going to put here and say Barnes Hut algorithm, and we're going to say the Barnes, come on, spell it right, method algorithm divides space into a neat. I actually don't know how to use those, so I apologize. Barnes Hut algorithm is divide space into a quadtree, an octree. Let's say octree in order to better approximate cut computational time without losing much precision in n-body simulations. If you want learn more soon, bug me about it. Okay. And we're also going to put a to-do here. Okay. Okay, so now we should have everything basically set and ready to go. I'm going to add the Barnes Hut algorithm to the summary here, and so Verlet integration, and we're just going to do yank paste and do Barnes Hut. Barnes Hut, and we're going to change this to Barnes Hut.md. Okay, write that, and everything should be online, so let's go ahead and refresh this page. Give it a second. Come on. Okay, and so we should just be able to click this guy, and it should lead us to Barnes Hut. This should lead us to Verlet integration. Yep, this should also lead us to Barnes Hut. Good, everything's there. Barnes Hut algorithm divides space into an octree in order to cut computation time without losing much precision in n-body simulations. If you want to learn more soon, bug me about it. Good. Okay, so that's what we have so far. Now there's one thing I want to point out that is here. I wrote something, but I don't remember what I wrote. If we take a sinusoidal function like sine of omega t or cosine of omega t, we find the curve that goes from plus minus 1 shown in figure 1a. Oh, I did not finish this. Prepend any copy or paste mode with R. Any copy or paste from that register. Oh, yeah. So I think I did know about this. Yeah, okay. I need to finish this. Yeah, I knew this. Good. Okay. Figure 1a and figure 1b. I just need two figures. If we take a sinusoidal function like sine of omega t, So shown in figure 1A. The real space figure 1B is in frequency space. Yeah, okay, so literally I just need to plot these guys. And then I have figure 1A and figure 1B, which need to be updated. Okay. So let's go into back here. And let's look for fig. Okay. I read about those in image processing. Wait, you read about what in image processing? So let's do git add. Where's the last git add? Here it is. Yep, okay. Let's do a quick git status. Yes, modified. Git diff Euler.md. Yeah, so let's do git add Euler.md. Let's also do git add Barnes Hut and Verlet. Git status. And I think, oh, git add summary, and that should be okay. Wait a minute, what's back there? VI mathematical background, and let's do differential equations.md. Oh, I don't have anything in there. Okay. I just want to say that I'm a freshman in university and studying computer science and just began reading your Git book. Oh, great. Again, I'm working on it, right? So this is a progress. Okay. Let me go ahead and commit this, and then I want to describe what this algorithm archive is one more time. Let's do an ls here, git status here, and now let's do git commit -m, adding, let's see, chapter 4 Verlet integration. Git push origin master. Why is it so many lines? Okay, I'll get an email in just a bit to make sure that this is working, but it should be online now for everyone to check. Again, all you have to do is go to the algorithm archive. You can just Google Arcane algorithm archive, and you'll find it. It's here. You just go to read. 1 second. And it'll be updated in like a few seconds or something. It's not here yet, but it should be there soon. It just takes a second sometimes to update. Let me see. I want to go to here. It should be... Oh, I need to sign in. Crap. Give it a second. 404, book not found. Great. All right. Let's do git book here. Come on. Arcane algorithm archive. It's just there. There we go. And we should be updating soon. I think it should be up. Ah, here it is. So now we have relay integration, which is what we just worked on. Euler methods. Again, put this up today. Barnes Hut, which will need to be done. Okay, so let's talk about where we want to go with this. So the Arcane algorithm archive is an archive of all the Arcane algorithms we go through, right? So that's kind of the idea. It's in a way a lab notebook, and the hope is to make it both user-friendly and descriptive. So people can read it, they can enjoy reading it, they can learn what they need to learn, and then they can move on to the next algorithm where it's kind of like a hobby book. It's a book for people who want to learn, but don't necessarily have the time to take a course on all the different algorithms and stuff like that. More than that, I kind of want it to be written by the community, you know, like it's one of those things that we have plenty of programming power here, like plenty of people know how to do programming. So I thought, okay, how about we give people the ability to write their own algorithm or write their own implementation in their own language, and whatever they want to implement, however they want to implement it, they give it to me, I review it, make sure it works, and then I put it up. So basically you guys, if you want to, can submit your own versions of code, and I can put it into the Arcane algorithm archive like I did at the bottom of here. I think, is it not in the channel? Ooh, I just deleted that. Meant to keep that up. Let me check. I think it might be. 1 second. So let's see. Info. What are you doing? Yeah, I'm currently gathering a bunch of algorithms into a notebook called the Arcane Algorithm Archive. This chapter on Gaussian elimination. Yeah, so I should do that. I'll put that in here. But basically, I'm going to put a video up on YouTube. Come on. I'm going to put a video up on YouTube, and at the end of the YouTube video, I'll say, hey, look, we have everything written for the Verlet algorithm, Verlet integration here, with exception of the example code, and this is your job to put in the example code. I will also put an example code implementation in here in just a bit, but that's kind of where we're at there. For now, I think we did everything we needed to do. We have the velocity Verlet algorithm here, we have Verlet integration there, and it's okay. It maybe reads a little bit funny. We'll have to go back through and check that up. But for now, I think it's okay. So I think I'll go ahead and end the stream here. And tomorrow, my goal is to work back on the scientific visualization library and get some stuff up and running there so that we can immediately take... I have implementation, etc. Yeah, that's fair enough. I mean, again, if you don't want to do it, you don't have to. It doesn't take too much time. It's just an interesting idea. What was I going to say? Some of those I had to implement in MATLAB. I'm sorry about that. Okay, so I think that's about it for today. I'm going to try to come back tomorrow. I have a couple things I want to do with the scientific visualization library to make it a little more robust and easier to use, and we'll try to do that tomorrow. So here's the thing though, I'm going to let you know right now, I'm 50-50 on streaming tomorrow. It depends on whether I can actually get everything prepared for stream. If I can't, I'll skip tomorrow. We'll see you next week. I'm going to do my best to stream tomorrow though, so we're 50-50 on that. Again, since I've come back, I want this to be more relaxed. I don't want to like force myself into like just frantically studying something the night before. This is basically my free time, and I want to make sure that it stays relaxed and fun and enjoyable and not something that I stress over. So that's kind of the idea there. So I'm going to do my best to stream tomorrow, let you know if I can and cannot. Outside of that, have a fantastic day, night, afternoon, morning, evening, whatever time it happens to be your time, and I will see you around next time for the next episode of Simuleos, when we either work on a new algorithm if it's next week, or we work on the scientific visualization library if it's tomorrow. So thanks so much for coming in, and see you around. Bye, guys.